Hi, I'm Professor Van Hamlin, and we're going to cover the quotient rule today. So if I have two differentiable functions, f of x and g of x, I want to be able to find the derivative of the quotient. So the derivative with respect to x of f of x divided by g of x is the derivative of the numerator multiplied by the denominator minus the numerator times the derivative of the denominator all over the denominator squared. So we'll do these four examples, and then I'm going to do a fifth example to where I have a quotient rule and a product rule mixed together. So first, let's go ahead and start with A. So if I want to take the derivative with respect to x of this quotient, I know that y prime, using the statement above, says I have to take the derivative of the numerator first. So the derivative of the numerator is going to be 3x squared. And then you have to multiply by the denominator just being e to the x. Minus the numerator, so the numerator being x cubed, times the derivative of the denominator. Well, the denominator and the derivative of the denominator end up being the same thing, because the derivative of e to the x will also be, e to the x. And this is all divided by your denominator, but I have to square it. So we're going to have e to the x squared. Now I'm going to simplify this. I noticed that the numerator has an e to the x in it, so I can factor out an e to the x, and I'll have 3x squared minus x cubed. Usually when I have this e to the x, squared, I would write this as e to the 2x, because when you raise an expression to a power, you're going to multiply the exponents. But I notice in this numerator that I have an e to the x out here. So, e to the x squared is e to the x times e to the x, which will make it nicer looking when I want to simplify. And I can see that, these e to the x are going to cancel to a product of 1. So this derivative is going to end up with 3x squared minus x cubed, all divided by e to the x. So next we'll do B, and we knew that B was the derivative with respect to x of the tangent of x. Now I chose this because this is a classic example of where the quotient rule kind of shines. So if I want to take the derivative of the tangent of x, I know that the tangent of x is built of two differentiable functions, the sine of x divided by the cosine of x. So y is the same thing as the sine of x divided by the cosine of x. So if I want to find y prime, again it says derivative of the numerator, so the derivative of the sine of x is cosine of x, times the denominator, which is going to be cosine of x, minus, with the top being sine of x, times the derivative of the denominator. Well, the derivative of the denominator, the derivative of cosine, is going to be minus sine of x. And this is all divided by that cosine x, the denominator squared. So cosine of x squared. And then we're going to simplify. So what I can see is that this is cosine times cosine, so this would be the cosine squared of x. Now I have a negative sine of x times a negative sine of x, so this is going to be plus sine squared of x, all divided by cosine squared of x. Now remember in the Pythagorean theorem that the sine squared of x plus the cosine squared of x is equal to 1, that this numerator is equal to 1, so this is going to be 1 over the cosine squared of x. So when you look this up in your calculus book, when you want to figure out what the derivative of the tangent of x, that 1 over the cosine of x is the same thing as the secant squared of x. So when you look that up, you're going to see that this is the secant squared of x. Which kind of helps. When you want to find the derivative of trig functions, you really only need to know the derivative of the sine of x and the derivative of the cosine of x, along with the quotient rule, and you can derive the derivatives of the other four trig functions. So the next one, we had another rational expression, of course, since we're doing the quotient rule here. So this is going to be the derivative of, I chose a polynomial over a polynomial, so that should have been b. This is now going to be c. So this is going to be x plus 3 all divided by x minus 4. So going back to the statement, we just have to, know the derivative of the top and the bottom, our numerator and denominator, and write them in the correct order. So again, derivative of the top. So y is going to be the derivative of the top. The derivative of x plus 3 is just going to be the derivative of x is 1. The derivative of 3 is 0. So this is going to be 1 times the bottom. So this is going to be a x minus 4 minus the top, which is going to be an x plus 3 times the derivative of the bottom. Again, the derivative of the bottom, this is going to be 1 minus the derivative of negative 4 is going to be 0. So this is going to be times 1 as well, all over the bottom squared. So we'll simplify this numerator. We can see that this is going to be 1 times x minus 4 is going to be x minus 4 minus, 1 times this, so minus x minus 3, so minus x minus 3, all over the bottom squared, which is going to be x minus 4 squared. Simplifying, you can see that, these x's will cancel in the numerator, so I'm going to get negative 7 over this. So we're going to have negative 7 divided by x minus 4 squared. Now the last main example I want to talk about, B and D, is going to be x squared divided by 5. When many students, they learn the quotient rule, and as soon as they see a division, they think that they have to use the quotient rule, immediately. Or basically always. So I'll show you this using the quotient rule, and this also kind of give you a heads up to say, well, maybe I could have done this an easier way instead of using the quotient rule. So y prime, we know it's going to be the derivative of the top, so 2x, times the bottom, which is going to be 5, minus the top, which is going to be x squared, times the derivative of the bottom. Well, the derivative of 5 is going to be 0. And this is kind of that heads up spot. When you're doing your product rule or quotient rule, if you take the derivative of the first or the second or the top or the bottom, and one of them ends up being 0 like this, it really means that you probably could have done this a different way, and I'll show you that way in a minute here. So don't forget, we still have to do g of x squared, so this is going to be 5 squared on the bottom, or 25. So simplifying, multiply by 0, that term is going to be gone. And so I'm going to have, 10x all over 25. Or if you wanted to simplify already, that you can see this 5 and one of these 5s are going to cancel. So really this is just going to be 2x over 5. So they're both divisible by 5. So this is going to be 2x divided by 5. Okay. Back to that simpler path. Well, I can see that the derivative of this denominator is going to be 0. So what that really means is I probably could have wrote this as coefficient, variable raised to a power. So this is the same thing as 1/5 times our x squared. And what we know is the derivative of a constant times a function is that constant times the derivative of the function. So if I wanted to take its derivative, you could have pulled out that constant and then just took the derivative of this function. So this is going to be a 2x. So simplified, we can see that 1/5 times 2x is 2x over 5. So careful using product rule and quotient rules, immediately. If you see that one of them 0, you probably could have pulled out a constant and made your life a lot easier. All right, the last one I wanted to cover, and I'll just call it E, is going to be 1 to where they're mixed. So I'm going to have find the derivative, but we're going to see that this is going to be a product rule inside of this quotient rule. And then last, what we'll do is I'll prove this quotient rule to you. So E is going to be x squared times the sine of x, all divided by the natural log of x. Now what we notice is that this numerator has a product in it. So when we take the derivative of the numerator, we're going to have to use the product rule. So remember that the product rule, if this was the derivative with respect to x of f times g, then it's f prime g plus f g prime. Just as a reminder. So y prime, we know we're going to need the derivative of the numerator. So quotient, this is going to be a product rule here. So derivative of the first times the second plus the first times the derivative of the second. So that's the derivative of the numerator. So that's our f prime. We still have to multiply this by, g of x, so natural log of x. Minus f, which was this product, so it's going to be x squared sine of x, times the derivative of the bottom, and I know the derivative of the natural log of x is going to be times, 1 over x. And this is all over that denominator squared. Brackets or parentheses really just to help it look a little bit nicer. So the only thing I really see simplifying here is this term over here that I have an x squared and then on the numerator and an x on the denominator. So I guess I could send this natural log of x through and expand as much as I want to, as much as I can. But I'll do that then. So 2x natural log of x sine of x plus x squared natural log of x cosine of x minus sine of x times x. So x times the sine of x. All over the natural log squared. All right. So next is going to be our proof of our derivative. So I'll pause it, I'll set it up, and then we'll get to it. All right, so let's prove this. So we're going to use the difference quotient to prove it. I know that the derivative of a function, say if this is an h of x here, then it's going to be h of x plus h, I guess that's a bad example, minus that function, all divided by h, but the limit as h goes to 0. So we know that this is going to be the limit as h goes to 0 of this function, but instead of x, it's going to be x plus h. So this is f of x plus h all over g of x plus h minus, this function with just x, so this is going to be f of x divided by g of x, and then this is all going to be divided by h. So in order to do this, what I need to do is simplify. We're gonna add 0 to this to create difference quotients that I'm actually looking for. So what I'm first going to do is I'm going to get common denominators for the numerator. So I'm going to multiply this fraction by g of x. I'm going to multiply this fraction by f of x. So this is going to be the limit as h goes to 0. This function times g of x is f of x plus h times g of x. Now they're going to have a common denominator of this product together. So minus, I have to do this one times g of x plus h. So f of x times g of x plus h. This is going to be now divided by the product of these things. So g of x times g of x plus h. This entire thing is being divided by h. So really, you can just put the h in our denominator. So h times that expression. All right. So what I want to do is I want to cleverly add 0 to this numerator. So this is going to be the limit as h goes to 0. So this is going to be f of x plus h times g of x. So what I'm going to do is I'm going to first add f of x times g of x. And I also have, so I'm going to subtract it first, then I'll add it second. I'm going to add it over here on the end because I want this expression to become first. So this is going to be f of x times g of x plus h. Now I still have to add this because I need it to be the exact same expression. So plus f of x times g of x. Now we still have, this all over, our denominator, which is going to be h times this expression. So h times g of x times g of x plus h. All right, now if you kind of notice, what I'm going to do is I'm going to group, you know, these two expressions just with h, and also these two expressions also with h. And I'll put this in the denominator to kind of hide it out of the way. So this is going to be the limit as h goes to 0. So this is going to be f of x plus h times g of x minus f of x times g of x. This is all going to be over h. Now I'm going to subtract because I want to group these two together, but I want this term to be positive and this term to be negative. So I'm going to say subtract f of x times g of x plus h minus f of x times g of x all over h. And we know that this thing is still being divided by this g of x times this g of x plus h. So all divided by g of x times g of x plus h. All right. So notice that, you know, this term here, you know, the numerator share g of x. So I could factor that g of x out of this. Over here, this is these two share this f of x, so I could factor that f of x out. And if I factor the g of x out, you can see this is f of x plus h minus f of x all over h. And if I factor the f of x out, you can see that this is g of x plus h minus g of x all over h. So really this is just g times f prime, and over here, this is f times g prime. Knowing that, you know, you can take the limit of every single term, so the limit of the difference is the difference of the limits, the limit of the quotients, the quotient of the limits. So I can send these limits all the way through. So this is going to be the limit as h goes to 0 of, I'm going to pull out that g of x, but I'll pull it on the other end. So f of x plus h times minus f of x all over h times our g of x minus the limit as h goes to 0 of g of x plus h minus g of x all over h, and I still have my f of x. And then this is all going to be divided by, boy, I hope this is still on the screen. This is all going to be divided by the limit as h goes to 0 of g of x times g of x plus h. You know, the limit of both of those. So, you can see. So notice that this is f prime, this is g prime. So what we get is that original quotient rule that says that this is going to be equal to, so I'll write it over here. This is going to be equal to f prime g minus f g prime all divided by, as h goes to 0, this is just going to be g of x. As h goes to 0, this is also going to be g of x. So this is g of x squared. So I don't need that bracket there. So, you know, this is what we're trying to prove. That is what we're trying to prove. And that's it. All right, I'll see you next time.